Alright, so I had a little bit of time here to hopefully run through the grasping gravity concept. So it says, how well does this model gravity? So it really doesn't, because the ball is falling at a constant speed. Looks a little laggy, but that's okay. It says, for this virtual field trip, let's set Beach Rio in as our backstage backdrop. So I'm going to go to backdrop, and they change these. Oh, Beach Rio right there. So you got Beach Rio, and we're going to change it to ball. Oops. And let's bring in the soccer ball for our sprite. So I go to import sprite. This is all different. Search. Ball. Well, they don't have the, oh yeah, soccer ball just looks different. Let's bring in this beach ball, why not? So I got this beach ball, and it says we'll be using the green flag, set it to 50%, so yeah, that one we could probably set to 50. So I'm gonna do green flag, set size to 50%. All right, and then so that's just the setup, and then it says task 1. Now we're going to try to model the ball being dropped from somewhere high and falling down onto the sandy beach. One way to start this is to test the mouse. One way to start this is to test if the mouse button has been clicked. If it has, then send the location of the ball to the position of the mouse. I'll let you figure out how to link these 4 blocks to achieve this. So I got to pull an if-then conditional. So I got to do blocks, control, if-then conditional. Mouse down, go to pointer. Forever loop. Okay. So obviously I want to test and see if the mouse is down. If the mouse is down, forever go to the pointer. No. Forever test. So if the mouse pointer's down, go to the mouse pointer. Forever do that. Link that in. And so now I can see that no matter where I click, the ball comes to there. I don't like this. I'm going to set it to 75%. Good. So no matter where I click, the ball goes there. I'm going to delete Scratchy out. I have this. So this is the setup. Is that part good enough? So it seems like then this GIF then tests is that part working. You can press the stop sign to turn your program off once you get this working. Next, let's get the ball modeling fall on a mouse click. Is it the X or the Y variable that is changing if the ball is falling straight down? Well, that's the Y direction, right? The Y direction goes straight down. One backdrop that's really helpful in seeing the math, aka the Cartesian grid, behind the scenes of the stage is the XY grid. In fact, change your background now just to make sure you understand this next bit of code. So I'll go to my stage and I'll set that to XY grid. Thank God they still have that. Task 2. Make sure you click back on the ball before writing code, so that would be important, right? Because we don't want to write the code for the backdrop. So of course you answered Y value to the previous question on getting the ball to move down. In order to control the drop, we're going to again have to piece together a few blocks and insert them into the previous code. Why does the ball fall the way it does? Why does it stop where it does? So it falls the way it does because the y value is constantly changing by 3. So this right here, this change y by -3. So I go to motion, change, I need to change y by, and I'm going to do change y by -3. I'm going to go back here. If the y position is greater than -130, so there should be a sensing here for the y position, right? And if that is greater than -130, we want to continue to change that. So that's going to be an if-then conditional with that block piece. So if this position is met, try to draw this arrow, link it back into your previous code without giving too much away. Maybe that's too vague, I don't know. So then I could do, if the y position is greater than -130, which is down here, so up here above that, then keep changing, and we'll put that inside the forever loop. So then it would drop until it hits the 130. Okay, so now we have the ball constantly dropping. I'm going to stop it. So that part might make sense. Hopefully you're still not convinced that the ball models gravity no matter how fast you make the ball drop. Oh, did I say that up here? So could you modify the code to make it drop faster or stop at a higher or lower location? So here, if I change this like to -5, well, let's just do something bigger, like -8. Then that would mean that the ball is going to drop that much faster. So now if I click, right, drops faster, I can make it so it stops higher, like -100 instead of 130. Alright, so now notice the center of the ball is stopping at a y height of 100. So there's that piece. Hopefully you're still not convinced that the ball models gravity no matter how fast you make it drop. This is because the force of gravity pushing the ball makes the dropping speed increase. That's why if I drop a penny on your head from 5 feet above, it will not injure you. But dropping one from the top of an Empire State Building may be deadly. So that's what we're trying to show here. So the speed is not the same if I drop from 5 feet as if I drop from the top of the Empire State Building. Task 3, a better model. Now the average person, when you see a penny or ball drop, sees no mathematics whatsoever. So what we're going to do next is make the numbers pop out, similar to the way you did by changing, similar to the way we did by changing the beach backdrop to a coordinate grid. Follow these steps. Step 1, from the data menu, make a variable called speed. So I'm going to go variables, make a variable, we'll call it speed. It's interesting though, it's not called the data menu anymore, it's just called the variables, right? So that's good. Place the set block to -3 at the beginning of your code script. Place the set block to the set speed block, right? So if I go here and I set the speed, stop this code and set the speed to -3 to start. That's an initial. Step 3, make a list using the button below your variable blocks and call it rate of change. So I'm going to make a list and I'm going to call it rate of change. Okay, so I have that. Place the add thing block within your loop and add speed change by speed. So right, so now I need to do change y by speed. So I'd put this in there. Do I say that anywhere specifically? drag the speed variable block into your change y block. So I missed that. And then it says make a list using the button below your variable blocks and call it rate of change. So now I have add thing or add speed to rate of change, and that's going to go under the change block. So if condition is met, then you're going to change the speed and you're going to add it to this list, right? So now I'm going to run that code, and notice that it keeps the value at -3. So you just, every time it does it, it's at -3. What do you see? What is it saying, and what would you want it to say? Well, it's saying that the speed is constantly -3 no matter what, right? So it doesn't matter where the ball is at in its drop process, the speed is at -3. Looks like we're going to want to add a delete all at the beginning of here every time we run it. I'm going to click stop, rerun. Hopefully I say that later. So, yep, so down here on the way, one way to get the speed to increase each time is by changing the value through each step, each pass of the loop, known as incrementing. Also, you will want to delete out all of the lists and reset speed to -3. Okay, from your list or table, what was the initial speed of the ball? Maybe I'm not explicit enough here. I should say one way to get the speed to increase each time is by changing the value through each pass of the loop, also known as incrementing. Also, you will want to delete out, so I'm not very explicitly saying to put that change speed by 1. So in here, this change speed by 1, that needs to be inputted into your loop. So each time you're looping through, you want to take the speed and increment it up by 1. So I would do that, and I would click the flag. Oh, increase the speed by -1, because otherwise it's going to start going up instead of down. Alright, so let me rerun this. Seems pretty fast. I'm trying to look at the drop speed. Changes by -2. Interesting. So this delete all maybe would go into the loop here. No, obviously not. Delete all. So every time you click it, the delete all. So that's tricky. So maybe it's just that last step that's not clear enough. And we need to reset the speed to -3 in there. So this set speed to -3 should go in that loop as well. Stop, run. There we go. So now it's like, well, what is this showing? It's showing that the speed no longer is constant. The speed is constantly changing by 2. So this rate of change is what is constantly changing. So it's like, if you look at a graph of a line, so if I went to just like Desmos, and I go to a graph of a line like y equals 5x plus 1. if you go to a line like this, you'd be like, oh, well, as you step up through the values, let me just make this a function to maybe make this clear. This we'll call f of x, and then we'll evaluate the function at, you can plot points on here like 2, 3, like plotting points, but instead of having a static point, you can, let's put a label on it. Instead of having it a static point, what you can do is run a variable point that will kind of scroll through your function. So we'll just make it a value, some variable like a, and then evaluate whatever that function, or whatever that a value is in the function. So again, all this means is the a value currently is set at 1. This point is 1 comma, and we're plugging 1 into the function. So we're evaluating, in this second y coordinate, we're evaluating f of 1. So notice how the list of values in terms of the points would go from, let's change this stepper to 1. So you start at 1, right? And then you go up to 6. So in terms of the y value, you changed by 5, right? Changed by 5, changed by 5. So you're constantly changing the y value by 5. So if you just looked at it from the perspective of the change in the y values, your constant rate of change in the y values makes it linear. However, if we made it something quadratic, like x squared, notice that if we went from 0, so just now focusing only on the y value, went from 0 to 1 to 4. So now you changed by 3, right? So you changed by 1, then you changed by 3. Now we changed the y value from 4 to 9, so we changed by 5. Then we changed by 7. Then we changed by 9. So it's like the y value is constantly increasing in its change value, and where you can see that is with the method of finite differences. Now that's also something from calculus, so I wanted to make sure, I should have put to search for algebra 2, but notice like even this one you can tell like, maybe let me pick a good one. I don't know if my video is not working, it won't matter, but like, so he's got these sequences up there. Look at this first one. The constant rate of change is 2, 2, 2, 2, 2. So think of these like outputs even though it's a sequence of numbers, these are like the y values, and the placeholders like the x value, right? So this is like 1, 3, 2, 5, 3, 7. Whatever it is, this constant rate of change that you see here in the first level of differences makes it linear. So if the difference is constant on the first level of the outputs, that is first degree or linear. If it's the y equals mx plus b. If the level difference is not the same, so notice here you went up by 7, up by 9, 19, up by 37, 61. Well, it looks like this one's going to be cubic because it's the third level of differences that are constant. Hopefully that last one is quadratic. Maybe he's not going to do that one. Yeah, he is. Oh, that is. Good. So notice that the y values are changing by 3 to 5 to 7 because it's constantly changing because the differences of the first level differences is a constant. That makes it quadratic. So here, right, the difference of these differences, so you go up from -5 to -7 to -9 to -11, so you're constantly going down by 2. That's like saying this is our first level of differences. The differences of these differences is 2. So that's what I was going for here, a way to show a side of quadratic that people don't usually see and how it can be modeled in gravity, because this drop is now more accurate to what an actual ball drop is because it's increasing in speed each time. So I don't know, that's what I was going for. I thought I'd just make this video quick to actually help me process through. Hopefully it makes some kind of sense, and we'll stop it there for now.